Hello, everyone. My name is Alena Rybakina, and I would like to talk about adaptive query optimization. Some information about me. So I'm a core developer in PostgreSQL, in Postgres Professional, and I have been working there since 2021. And I have made some contribution to the PostgreSQL, and my part is author-any transformation, and I have participated in extension development like EQO, Surplan, and replanning. So my outline of the talk consists of the following elements. First of all, we will speak about how does adaptive query optimization work. We will discuss problems and features that we had during our EQO development. I'll show you some examples and testing results. So how does EQO work? Adaptive query optimization is an extension and improves cardinality estimation, and it can help optimizer to find more optimal plan. Its procedure is to save the real cardinality information and use it in the future. Let's consider some optimization issues. Needless to say that optimizer has some problems which related to the cardinality estimation. So it needs always to use actual statistics to avoid it, and it perfectly works with a small number of joins in the query, and unfortunately it has an assumption about uniform distribution between columns. So what issue do we have? If optimizer evaluates cardinality incorrectly, it uses this information to estimate cost, and unfortunately it leads to the choice a suboptimal plan. And so we have a lot of issues related to the choice a suboptimal plan, but we are engaged in improving the assessment of cardinality. These issues are discussed in this article, so you can find more information about it here. And nevertheless, there are some solutions from PostgreSQL database, and I think the most popular one is extended statistics. It has theoretical guarantees that the assessment of cardinality will be improved, but at the same time, it requires a lot of memory to store statistical information about data, and the occasional updates are required. And so we have alternative solution to fix this problem, and it is the memory for planner. So it can store an actual cardinality in the storage, and it shares this information with the optimizer next time. And but we need to store information about selectivity, because optimizer needs to determine whether cardinality is appropriate for current selectivities. And it should update the data from time to time. So it is the main idea that EQO is based on. Let's discuss the model description of EQO. Every node is described through cardinality, selectivity information. I think it's obvious. But at the same time, we need to store information about relation ID, clauses. So you can see an example on the left of the slide when we describe 3 nodes, nested loop, and 2 sequence counts. And we determine information about them like relation IDs, selectivities, and clauses. All conditions in the node that differ only in constant are equivalent for us, like two examples, two queries that differ from each other only in constant. And so we call neighbors as the closest nodes based on R2 distance. And imagine the situation when we try to estimate the cardinality information for black smiling face. So we find 3 neighbors for them. And first of all, we need to calculate the distance between 3 red smile face and the black one. We did it because we need to calculate the contribution of these neighbors to evaluate the cardinality for black smile. So you can see that the contribution for the left smiling face is the smallest one because it has because it is farthest from the black smiling face, while the red smiling face with W3 sign has the biggest contribution because it is the closest to the black smiling face. So we define the number of rows as a weighted average of the cardinalities of neighbors. And to achieve it, to build our model, we use k-nearest neighbor method, and our learning workflow consists of 2 stages. After the execution stage, AQO collects information about cardinalities, selectivities, and it adds it to the storage, and it can learn from them. On the planning stage, the model uses this information to predict the cardinality for the current node. And we use math for learning. And the first one is loss function. It evaluates the discrepancy between predicted and actual rows, or it is cardinality error. And it is a main component of AQO learning because model optimization process is aimed to minimize losses. And stochastic gradient helps us to optimize data in the train set. AQO has several components, and the first one is AQO data. It's like storage that store information about selectivities and cardinalities of nodes. And the second one is AQO queries. It stores information about settings for every node. Because I'll explain you why it is important for us later, and you understand it. You will understand it. And AQO query text stores information about query ID and query text. And the last one is AQO execution statistics. It stores information about query planning time, execution time, and cardinality error. With and without AQO. I'll explain you why it is important later. So I think we all know how optimizer works, but if anybody has some questions about it, I answer it. And so I just want to point out that 2 components of AQO are located in analyzer stage, and it is AQO queries and AQO query text. They help us to determine is query query is known for AQO or not. If a query is known, AQO processes it according to the setting. If it is not, it only adds information about this query in the storage. But I suggest considering the second part of optimizer, and it is highlighted in red square. So you can see path generator. When path, the first component here, when path generator tries to generate an optimal path, it needs to estimate cardinality information of nodes. And it uses statistical information about every expressions assigned for the nodes. And it uses this information to evaluate cost information about node to determine this node is too expensive for us, and maybe we need to exclude it from further consideration. And so when path generator generates an optimal path, plan generator uses this information to generate the plan, query plan, and query executor executes it. The results is sent to the user. So as I mentioned before, the first workflow of AQO is learning. So when query executor finishes its procedure, AQO collects information about selectivities and cardinalities. On this slide, features is selectivity. So I'll continue. And if AQO if AQO knows this query and this query, it brings out information about cardinalities and selectivities, and it calculates the discrepancy between real cardinality and old ones, and runs a learning procedure. So when path generator tries again to generate an optimal path, it uses information from AQO, but it does not estimate the cardinality information again. And we will hope that a query plan will be better. And the last component is AQO execution statistics. So as I mentioned before, AQO execution statistics collects information about planning time, execution time, cardinality, why it is important. So the user can use this information to determine whether query is whether query works better with AQO, and so we can adjust some setting for the prediction, for example. Or we need to disable the AQO for this query, because some queries, because AQO does not help some queries. And besides this information, AQO uses too in automatic mode. When it decides whether query is ready for prediction, or they need to be learned more period. And so we used hooks for development AQO, and these hooks we added to the PostgreSQL database, and they help to share information about cardinality information between optimizer and AQO. And this hook we added too. It helps us to visualize information about query plan, and mostly we use it for debugging. Let's discuss problems and features. So the first problem was related to incompletely executed node, and it is caused by the presence of a limit node in the query plan. And another reason is there are no rows in one of the subnode of the connection node. We decided that AQO does not use this information for learning because we can't trust this information. And to be honest, it is actually in progress. And the last reason is when is a query execution time limit. For example, we set statement timeout parameter. And so I think it is a similar schema, but we see another new component, and it is statement timeout. When query executor finishes its procedure, yeah, I repeat it. So it is in the main workflow, AQO collects information about selectivities and cardinalities. So if AQO sees that the node was not completely executed, it set reliability parameter as 0.9. And AQO does not consider this information for prediction because, but it remembers it because we hope that when query will execute again, we can update this information and we'll use it finally. So, and the second problem was related to lookalike feature. Imagine the situation when we had a lot of information about queries, but they differ in structure. So basically, AQO doesn't consider these queries to predict cardinalities. But lookalike feature can help to avoid it. But AQO needs to consider neighbors only with the same relation ID and number of clauses to avoid collisions. Now I'll show you some examples. But before this, I described what database I used for my experience. This database describes the situation when students try to take the exam. And some of them write essay, and we collect information about word counting. It is a text-len column. And some students have a preliminary course before taking an exam. And it is a test preparation column here. You can find more information about this database if you follow the link. And to simplify the concept of the query plane with AQO, I'll explain you some AQO terminology, and it is feature space and feature subspace. So feature space is the space that collects information about queries, and feature subspace is a subspace of the feature space that collects information about cardinality, selectivity of every node for every query. Might be it's difficult. Let's consider some examples. You can see three different queries. Two of them differ only in constants, and they belong to one feature space. The third one differs in structure, and it belongs to another feature space. And we can several ways to execute student table. So you can see that index scan nodes belong to one feature subspace, while sequence scan has another type of execution, and it belongs another feature subspace. I hope it is clear. And so the first problem that I had is related to functional dependencies. If you look at the table, it's okay. You can see that test preparation and degree has a high correlation here, and it leads to underestimation. So when a QO fixes this problem, I considered that query plan hasn't changed. But in another problem, which related to non-uniform data distribution, so you can see the diagram that shows data distribution for word counting column. And so when we try to find information about average degree for every group, we see underestimation problem again. But when a QO fixes the cardinality information, our query plan has changed. And our connection condition was pushed down to the index-only scan node. And some nodes, like hash join and merge join, transform to the merge join and nested loop. So I think our query plan will become better. And the last problem was related to outer join. Let's imagine the situation when we had a lot of some students who failed the exam, and we created a new table for them. And now, when we try to compare information about their last degree and the current now, we see, and we use outer join there, we see underestimation problem. AQO fixes it, and we see our query plan has changed. Our push down to condition was moved to the merge join and became a join condition, and two nodes nested loops transformed to the merge joins. But let's consider this query plan again. You can see that sequence scan produced less number of rows that third node produced it. It is an interesting feature because, to be honest, I saw that in the code, third node takes number of rows from sequence scan and other subnodes as it is. And so, unfortunately, my customer had a similar problem, but it was worse. His sequence scan produced about 200,000 tuples, while third node produced about 1.5 billion tuples, so it's really big. And out of my curiosity, I wrote the community this question, what happened? And so the reason is the merge join procedure. So when the merge join rewinds, its inner side to the start of the current group of equal key tuples, whenever it sees that the next outer tuple must be joined to the current group. And so due to the fact that explain counts the number of tuples returned from the node, it counts it twice. And so the more tuples we have in outer join, the bigger the effect. And you can see about this problem if you follow the link. As I mentioned before, there is a QO query stats, and it helps the user to understand whether query works better with a QO or not. And it is an example how it visualizes. And so this query helps to adjust a new setting for the query. And you can see that you need to set information about feature space or query ID and feature subspace or node ID. And set information about settings like is it learning? It will be learned in next times. In next times, okay, and or it is ready for prediction, or maybe you choose or customer chooses auto-tuning. There is a QO storage structure. Maybe it helps the customer or maybe you to find more information about a QO functionality. To be honest, there are a lot of components wrote in the documentary of QO. And testing results. I used a joint northern benchmark or Internet Movie Database to test how a QO works. And so it consists of 113 queries. And it is difficult for optimizer because it has a lot of joint connection, a lot of joint connection and correlations. There is a schema of joint order benchmark. And so I set parameters like random and sequence page cost as 1 from joint collapse limit as 4. And it worked for all stages. And I disabled parallelism during my during learning stage, and I enabled it when I compare the execution time between the original version of PostgreSQL and the patched one with the QO. So in disabled mode, execution time is high and stable, while in learn mode, execution time was volatile, but you can see that cardinality error was dropping, and finally it reaches about 0 value for all queries. And this diagram shows the difference between cardinality execution time without a QO and with it. So original version of PostgreSQL and patched one it with a QO. And besides, this diagram shows the ratio between execution time without and with using a QO. You can see that about 10 queries quadrupled in speed, about 11 doubled in speed, and unfortunately 2 queries, as I remember, it's 5C squared and 6A, but I'm not sure. Their execution time was increased. And speaking of other queries, they had no significant changes. In conclusion, QO stores statistical information about execution time, and it improves cardinality estimation, and it might be helpful to optimizer to search for the more optimal plan. And it is useful for complicated queries with the same structure and for a lab-like queries. On the other hand, QO works well when data distribution does not change rapidly, and if a database have a few number of temporary tables. We have some plans how we can improve QO. And first of all, QO doesn't learn on replica, and it ignores nodes with temporary tables. Speaking of other problems that we will try to fix, I talked about them before. If you have questions about them, I'm ready to answer. And you can find the AQO extension if you follow this link. And thank you very much for your attention. And I'm ready to answer the questions. Yes?
Do you have like configuration limits on how much data you keep through your run in the AQO data store for when you're tracking all the statistics and stuff like that? Do you cap how much data you keep to learn on?
You spoke about AQO statistic information?
So as you run the queries, you're basically recording cardinalities and statistics about the queries that you run. And you keeping that information around to learn on to improve future queries, right? How much data will you keep around?
Yeah, I understood your problem or your question. It depends on the parameters that you can set for AQO, first of all. But as I mentioned before, the default one is about 10,000 maybe, but I'm not sure. Yes?
Does AQ consider the possibility of a parallel worker in the query? How does it?
How you can consider is query plan will be improved or not? You speak about this?
Just wondering, sometimes the planner may choose to use parallel workers to execute a query, and I'm not sure how that kind of relates to the AQO.
Yes, your answer was related to the fact that I disabled parallel during learning. No, you can stay parallelism, but unfortunately, do you know how parallelism is not stable during cardinality estimation? Because every works can bring unpredictable number of rows, unfortunately, and it is some problem for AQO because it does not foreseen what cardinality will be. But AQO can learn with parallelism, but it takes longer time. Yeah.
The really important thing is joint selectivity, right? So wouldn't that be largely independent of parallelism?
Can you repeat the question? Sorry.
Well, I would imagine the most important thing would usually be the selectivity of joins, right?
Yes.
That is, of course, what the join benchmark is mostly focusing on. So I would think that that would be something that could be measured independent of the use of parallelism, at least in principle, if not in this particular case.
I can't.
You're saying that the use of parallel workers doesn't change the fact that the selectivity estimate is either good or bad. It's, it shouldn't really matter, should it?
No, I disagree with you, to be honest, because sometimes parallelism, because of unpredictable cardinality estimation, it is.
Right, but why would that have consequences for in practice? I'm not seeing.
Okay, understood. To be honest, I saw the situation when AQO needs more iteration for learning. No, for example, without parallelism, it takes about 15 iteration. With parallelism, it takes 50 iteration, and it is related, as I understood, that optimizer. No, it is related to the fact that workers. You can't predict what number of rows will be returned to the one worker. because it might be 2, might be 5, might be 100, might be because it is related to the
tendency for workers to have some kind of bias that they. I'm trying to imagine what that would be. I'm sure that's possible. I just don't know what that would look like. Thomas, help me out. What do you?
I think there is some sort of unpredictability in how we exactly report the numbers from the workers. I think
That sounds totally believable, but that probably could be.
Yeah, but I mean, like, that's where AQO actually is getting the information, right? So if it's getting like,
Is that the only issue, though?
I mean, like, I don't know. I know exactly what you know, right?
Okay.
So
It seems.
that would be.
I'm not denying that there could be a problem like that. That seems believable. I just don't know what it would be. Like, there was some disparity, significant disparity. But if that was the case, it would be nice to fix that anyway, because that seems counter to.
Yes?
It looks like you identify a particular query by taking the query text and hashing it. But you earlier said that queries that differ only in the constants will all be considered the same query. How much can I change a query and still have AQL recognize it as the same query? For example, if I change, for example, like a table alias, will AQL consider that a different query or the same query?
Okay, you modified table, yeah?
Like just the alias.
Values.
Like if I say like select from foo as A and then I change it to select from foo as B, is that the same query or a different query?
No, you use different tables, and it is this query is different structure.
Okay.
But if you, for example, select from A where x equal to 1 and select from A where x to 2, for example, they are similar. Yeah. Yes?
So you collect data in the execution phase and you feed it to the ADO data. That goes back to the cardinality estimation.
It depends on the mode of the AQO. For example, if your default mode is learning, it considers all new queries and it collects information about cardinalities of these queries. But for example, if you use the mode like frozen, you use AQO to predict the cardinality for known queries and you ignore new ones.
But this data is only available for better estimation of query execution, right?
Okay, can you repeat it? Sorry.
So the data that you collect is only useful in the next planning, or planning the next query, right?
When you run a query again. Runs query again, sorry.
Yeah. So there is maybe a very minor thing. So the concept, naming the concept as adaptive query optimization is colliding with the concept that I think you referred to Thomas Neumann in the beginning in one of the references, where they plan for long-running queries.
Yes.
They switch the plan for the same query. So
yes, it helps for queries with a lot of number of joins and with cardinality estimation problem. Yes?
We tried benchmarking, like finding out what the impact of enabling AQO in learning mode, for example, is on the throughput or on the system resources.
Okay, you asked me about other benchmark were used for testing here.
How much does it cost to enable this extension and to have it capture my workload?
To be honest, as I mentioned before, because why I said to mention before, because other team to continue developing this project, and so about a year ago it takes 10% of of additional, I'm not sure, productivity, no productivity. Yes, yes. But now it's, as I listened from my colleagues, they achieved the results that it fall down to maybe 2% or about it. Okay, thank you for your attention again.